This video contains audio content only. There are no visual elements or images accompanying the audio. If you're expecting to see video footage, please note that this is an intentional audio-only presentation. We recommend listening to this content rather than watching the screen. Thank you for your understanding and enjoy the audio. Welcome. Join us as we unravel the mysteries of the Omomyids, fascinating primates from the Eocene epoch. In simple terms, we'll explore their diverse world, from their unique physical characteristics and sensory adaptations to their varied diets and intriguing lifestyles. We'll delve into their evolutionary history, examining their place on the primate family tree and the ongoing debates surrounding their origins. Get ready to journey back in time and discover the crucial role these ancient primates played in the dawn of primate evolution. Chapter 1. Dawn of the Primates. The mysterious Omomyids emerge. Imagine our planet 55 million years ago, a world dramatically different from the one we know today. The Eocene epoch had just begun, a period of intense global warming known as the Paleocene-Eocene thermal maximum. Lush rainforests stretched across continents, reaching far north into regions that are now temperate or even polar. Mammals, recently liberated from the shadow of the dinosaurs, were undergoing a spectacular diversification, radiating into a dazzling array of forms. In this vibrant, evolving world, a new lineage was quietly emerging, high in the branches of the ancient forests, the Omomyids. These intriguing creatures, the earliest definitive primates in the fossil record, marked a pivotal moment in evolutionary history, the dawn of the primate lineage. While not our direct ancestors, they offer a fascinating glimpse into the early stages of primate evolution, a time long before the appearance of monkeys, apes, or humans. They were small, some no heavier than a chipmunk, flitting through the canopy under the cover of darkness, their large, owl-like eyes adapted for nocturnal life. Others evolved to a surprising size, reaching weights of 1.5 to 2 kilograms, about the size of a small house cat, and adopted a diet of fruits and leaves. The Omomyids weren't a uniform group. Their physical characteristics varied considerably, reflecting the diversity of their ecological niches. Many possessed shortened snouts and dental arcades, a feature that distinguishes them from other early mammals. Their anterior premolars were absent, and their cheek teeth displayed specializations for different diets. Some, with sharp, pointed teeth, were clearly insectivores, while others, with broader, flatter molars, were equipped to process fruits and even leaves. Like primates today, they possessed grasping hands and feet, their digits tipped with nails rather than claws, allowing for a secure grip on branches. Intriguingly, some species even sported a toilet claw, similar to the grooming claw found in modern lemurs, adding another layer of complexity to their fascinating anatomy. One of the most remarkable aspects of the Omomyids is their Holarctic distribution. Their fossils have been found across North America, Europe, and Asia, indicating they thrived across the northern continents during the Eocene. They shared this widespread distribution with only one other primate group, the Adapiforms, highlighting their significance in the Eocene primate world. The appearance of these two distinct primate lineages so early in the Eocene suggests a rapid diversification following the extinction of the dinosaurs, a period of evolutionary experimentation that shaped the primate family tree. However, the precise origins of the Omomyids and their relationship to other primates remain shrouded in mystery. Their skeletal anatomy, while undeniably primate-like, retains many primitive features, making it difficult to definitively place them within the primate family tree. The debate centers around their classification. Are they stem haplorhines, basal members of the group that includes modern tarsiers and anthropoids, monkeys, apes, and humans? Are they stem tarsiforms, an early offshoot of the tarsier lineage? Or are they stem primates more closely related to adapids than to any living primate group? Adding to the intrigue, individual Omomyid genera exhibit unique skeletal specializations that offer clues to their lifestyles. Necrolemur, for example, possessed fused lower leg bones, tibia and fibula, a characteristic shared with modern tarsiers, suggesting a similar propensity for leaping. These skeletal variations, coupled with the diverse dental adaptations observed across the family, paint a picture of a dynamic group adapting to a range of ecological roles in the Eocene forests. Even their teeth, preserved as fossils in ancient rock formations, tell a complex story. The unique structure of the Omomyid ear region, including the presence of an intrabular, ectotympanic bone, sets them apart from other primates. The significance of this characteristic and its implications for their evolutionary relationships are still being investigated. The presence of a gap between the upper central incisors, presumably indicating a rhinarium and philtrum to channel fluids into the vomeronasal organ, further adds to the puzzle of Omomyid adaptations and behavior. The Omomyids represent a crucial chapter in the story of primate evolution. Their appearance at the dawn of the Eocene, their diverse adaptations, and their widespread distribution make them key players in the unfolding drama of primate origins. However, their place within the primate family tree remains a source of ongoing debate, a puzzle that continues to challenge paleontologists. In the next chapter, we will delve deeper into the complexities of Omomyid systematics and evolutionary relationships, exploring the different hypotheses that attempt to unravel their place in the primate family tree and setting the stage for understanding the remarkable journey of primate evolution. Chapter 2. Bones of Contention. Unraveling the Omomyid Enigma. The Omomyids, those enigmatic primates of the Eocene epoch, present a formidable challenge to paleontologists seeking to classify them. Their delicate skeletons, often fragmented and incomplete, whisper secrets of an ancient past, yet these very clues spark passionate debates and controversies that continue to shape our understanding of primate evolution. One of the central debates revolves around the Omomyids' position within the primate family tree. Are they stem haplorhines, an ancestral group that gave rise to the lineage containing modern tarsiers and anthropoids, monkeys, apes, and humans? The large eyes of some Omomyids, reminiscent of tarsiers, seem to support this hypothesis. Furthermore, some share a fused tibia and fibula in the lower leg, a trait also seen in tarsiers, hinting at a shared ancestry and similar leaping abilities. Necrolemur, a European Omomyid, exemplifies this characteristic, leading some to propose a close link between Omomyids and tarsiers. However, the primitive skeletal anatomy of Omomyids complicates this picture. They lack many of the skeletal specializations found in modern haplorhines. For example, living haplorhines have a significantly reduced canal for the stapedial artery, a branch of the internal carotid artery that passes through the ear region. Omomyids, however, retain the larger, more primitive canal. Similarly, the path of the promontory branch of the internal carotid artery differs between Omomyids and modern haplorhines. In haplorhines, this artery routes through the auditory bulla, a bony structure in the ear, while in Omomyids, it takes a different course. These differences, among others, raise doubts about a direct ancestral relationship between Omomyids and haplorhines. Another hypothesis positions Omomyids as stem tarsiforms, an early branch of the tarsier lineage. This view emphasizes the similarities between Omomyids and tarsiers, such as the large orbits and, in some cases, the fused tibia and fibula. However, Omomyids also lack many of the derived features characteristic of modern tarsiers. For example, modern tarsiers have extremely large orbits, a large suprametal foramen, an opening in the skull related to blood circulation in the ear region, and extreme postcranial adaptations for leaping. While some Omomyids, like Shoshonius, possess relatively large orbits and a possible suprametal foramen, the contents of this foramen are unknown, making it difficult to draw definitive conclusions. Moreover, most Omomyids lack the extreme leaping specializations of tarsiers. A third hypothesis proposes that Omomyids are stem primates more closely related to adapids, another extinct primate group, than to any living primate. This view highlights the primitive features shared by Omomyids and adapids, distinguishing them from modern primates. However, this hypothesis has gained less traction in recent years, with growing evidence favoring a closer relationship between Omomyids and haplorhines. Recent research suggests that Omomyiforms might be a paraphyletic group, meaning they represent a collection of organisms that share a common ancestor but don't include all of that ancestor's descendants. This would make them stem haplorhines, placing them at the base of the haplorhine lineage but not including all of its members. Adding to the complexity, new discoveries continually reshape our understanding of Omomyid systematics. The discovery of Pseudolurus pyrenaicus in the Pyrenees Mountains of Spain offered valuable insights into the evolution of the Pseudolurus genus. This new species exhibits features intermediate between Pseudolurus isabinae and Pseudolurus parvulus, suggesting an evolutionary transition between these two species. Specifically, P. pyrenaicus possesses a thickened paracristid, a ridge on the teeth, lacks a distinct paracanid, a cusp on the lower molars, and has a well-developed buccal cingulate, a shelf-like structure on the teeth. These dental characteristics, combined with the size and shape of other teeth, help solidify its position as a transitional form within the Pseudolurus lineage. Similarly, the discovery of Necrolemur anedoni in Spain clarified the evolutionary relationships within the Necrolemur genus. This small-bodied primate exhibits features intermediate between the older Nanopithecus filoli and the more recent Necrolemur antiquus. The size and morphology of its teeth, particularly the lower molars, distinguish it from other Necrolemur species. N. anedoni has weak enamel wrinkling, lower molars with a narrowed trigonid, the front part of the tooth, a distinct paracanid on the first lower molar, and a relatively short hypocanulate lobe, a part of the last lower molar. These dental features, along with other skeletal characteristics, place N. anedoni as a crucial link between Nanopithecus and later Necrolemur species. More recently, discoveries in Texas and Utah have further illuminated Omomyid diversity. Two new species, Auraya lamporia and Mytonius hobsoni, were identified, adding to the growing list of known Omomyids. Auraya lamporia, from the Uinta Basin of Utah, and Mytonius hobsoni, from the Tornillo Basin of Texas, are both larger-bodied Omomyids, likely adapted for a diet of fruits and leaves. Their teeth reveal distinct characteristics that differentiate them from other Omomyids, contributing to the recognition of three distinct genera within the family: Auraya, Mytonius, and Diablomomys. These discoveries not only expand our knowledge of Omomyid diversity but also highlight the challenges in classifying these primates, as previously, researchers debated whether these fossils represented one, two, or three separate genera. The classification of Omomyids remains an ongoing endeavor, a testament to the ever-evolving nature of scientific inquiry. Many questions remain unanswered. What are the precise phylogenetic relationships between different Omomyid genera? How did they diversify and disperse across the northern continents? What were their ecological roles, and how did they interact with other Eocene mammals? Future discoveries, both of new fossils and new analytical techniques, hold the key to unlocking the remaining secrets of the Omomyids. Detailed analyses of skull morphology, including the eye sockets, nasal regions, and ear regions, could provide crucial insights into their sensory adaptations and evolutionary relationships. Studies of postcranial skeletons, focusing on limb proportions and joint morphology, could shed light on their locomotor styles and ecological niches. Furthermore, advanced molecular techniques, if applicable to fossilized material, could potentially revolutionize our understanding of Omomyid phylogeny and their place within the primate family tree. The Omomyids, those elusive primates of the Eocene, continue to challenge and inspire paleontologists, reminding us that the quest to understand our evolutionary past is an ongoing journey of discovery. Chapter 3. Whispers in the Eocene Night: The Sensory World of Omomyids. As the sun dipped below the horizon in the Eocene epoch, casting long shadows across the lush tropical forests, the world of the Omomyids came alive. These early primates, masters of the night, possessed a suite of sensory adaptations that allowed them to thrive in the darkness. Their large, forward-facing eyes, prominent in genera like Tetonius, Shoshonius, Necrolemur, and Microchirus, were not their only tools for navigating the shadowy realm. A closer look at their delicate skulls reveals further clues to their nocturnal prowess. The gap between their upper central incisors, a feature often overlooked, likely points to the presence of a rhinarium, the moist, naked surface around the nostrils seen in many mammals, and a philtrum, the groove that connects the nose to the upper lip. These structures are associated with a keen sense of smell, suggesting that Omomyids relied heavily on olfactory cues to navigate their environment, locate food, and perhaps even communicate with each other in the darkness. Imagine the tapestry of scents that filled the Eocene night: the sweet aroma of ripening fruits, the musky odor of other animals, the damp earthiness of the forest floor. For the Omomyids, this olfactory landscape was as vivid and detailed as the visual world we experience during the day. Their world was primarily arboreal, a realm of towering trees and tangled vines. Except for the specialized toilet claw used for grooming, similar to that of modern lemurs. These nails provided a secure grip on branches, enabling them to climb, scramble, and leap with agility. However, not all Omomyids moved through the trees in the same way. This skeletal specialization allowed it to launch itself across gaps in the canopy, covering distances with a single bound. Picture necrolemur, a small, agile creature with large, luminous eyes, springing from branch to branch, its movements precise and efficient. In contrast, Omomyids, lacking these leaping specializations, likely moved through the trees with a more deliberate, quadrupedal gait, similar to modern dwarf and mouse lemurs. Its skeleton, more akin to these living primates, suggests a lifestyle of careful climbing and clambering, exploring the finer branches and crevices of the forest. This diversity in locomotor styles reflects the varied ecological niches occupied by different Omomoyid species. The leaping necrolemur, able to cover large distances quickly, might have specialized in hunting insects or gathering fruits scattered across the canopy. Omomyids, on the other hand, with its slower, more deliberate movements, might have focused on exploiting resources in a smaller area, carefully picking insects from leaves or extracting nectar from flowers. The Eocene forest, a complex and multi-layered ecosystem, provided ample opportunities for different Omomoyid species to thrive, each with its unique adaptations and strategies. The nocturnal habits of most Omomyids are clearly indicated by their large orbits, those prominent eye sockets that dominate their skulls. These large eyes, optimized for gathering the faintest glimmers of light, allowed them to see in the dimly lit understory, where they could avoid diurnal predators and exploit resources unavailable to their daytime competitors. The structure of their middle ear, though lacking the anterior accessory cavity seen in modern haplorhines, reveals intriguing details about their auditory adaptations. The presence of an anterior septum, a bony structure in the middle ear, and a lateral septum forming a passageway between the middle ear and nasopharynx, suggests a complex auditory system, perhaps tuned to the specific frequencies of insect calls or the rustle of leaves signaling the approach of prey or predator. Yet, the Omomoyid story is not one of uniform nocturnality. The discovery of Runia in Texas, with its noticeably smaller orbits, presents a fascinating exception to the rule. This Omomoyid, unlike its large-eyed relatives, appears to have embraced the daylight hours. What evolutionary pressures might have led to this divergence in behavior? Perhaps Runia occupied a different ecological niche, one where diurnal activity offered advantages, such as access to different food sources or reduced competition with other nocturnal primates. Its smaller eyes, though less suited for the darkness, might have provided sharper vision in daylight, allowing it to detect predators or locate food more effectively. The presence of Runia underscores the adaptability of Omomyids and their capacity to evolve and diversify into a range of ecological roles. The Eocene night was a symphony of sounds, smells, and movements, and the Omomyids were integral players in this nocturnal orchestra. Their large eyes, keen sense of smell, and specialized hands and feet allowed them to navigate the darkness with confidence. Their diverse locomotor styles, from the leaping necrolemur to the more deliberate Omomyids, reflect the variety of ecological niches they occupied. And the discovery of the diurnal Runia adds a layer of complexity to our understanding of Omomoyid evolution, highlighting their adaptability and resilience in the face of changing environmental pressures. These small, unassuming primates, though long extinct, offer a valuable window into the early stages of primate evolution, a time when the foundations of our own lineage were being laid. Their story, whispered in the Eocene night, continues to resonate with us today, reminding us of our deep connection to the ancient forests and the remarkable journey of life on Earth. Chapter 4. The Adaptable Feast, exploring the diverse diets of Omomyids. The Eocene epoch, a period spanning from 56 to 34 million years ago, was a time of lush tropical and subtropical forests teeming with life. Towering trees draped with vines offered a rich tapestry of food resources, from succulent fruits and flowers to a plethora of insects. Amidst this abundance thrived the Omomyids, a diverse group of early primates whose dietary adaptations played a key role in their evolutionary success. Their story is one of remarkable adaptability, a testament to their ability to exploit a wide range of food sources in the Eocene ecosystem. Omomyids displayed a fascinating array of dental characteristics, reflecting their diverse dietary preferences. Their cheek teeth, the molars and premolars used for grinding and crushing food, varied considerably in shape and size. Early Omomyids, generally smaller than 500 grams, like Tetonius, Shoshonius, and Necrolemur, possessed cheek teeth adapted for a mixed diet of insects and fruits. Their molars were relatively unspecialized, with sharp cusps for piercing insect exoskeletons and broader basins for crushing softer fruits. The loss of anterior premolars, a defining characteristic of Omomyids, may have created space for more efficient chewing of insects. Imagine these diminutive primates, their large eyes gleaming in the dappled sunlight filtering through the canopy, delicately picking insects from leaves or savoring the sweetness of ripe berries. However, as some Omommyid lineages evolved larger body sizes, their diets shifted. Macrotarsius, for instance, tipping the scales at over a kilogram, transitioned to a diet primarily composed of fruits and leaves. This dietary shift is reflected in its dental morphology. The molars of Macrotarsius are larger and more robust than those of its smaller relatives, with flatter cusps better suited for grinding tough plant material. Similarly, Oraya, another large-bodied Omommyid reaching weights of 1.5 to 2 kilograms, adopted a frugivorous or folivorous diet. The ability to process leaves, a food source abundant in the Eocene forests, may have provided a significant advantage to these larger Omomyids, allowing them to exploit a niche unavailable to their smaller, insectivorous cousins. This transition to herbivora likely involved not only dental adaptations but also changes in gut morphology and digestive physiology to accommodate the fibrous nature of leaves. The shearing potential of molars, a measure of their ability to slice and shear food, provides further insights into Omommyid diets. This potential can be estimated by analyzing the shape and arrangement of molar cusps and crests. Sharp, pointed cusps and well-developed shearing crests indicate a greater capacity for processing insects, while flatter cusps and broader basins suggest an adaptation for crushing fruits or leaves. Teilhardina americana, a small, early Eocene Omommyid, exhibits molars with sharp cusps and a high shearing potential, pointing to a primarily insectivorous diet. In contrast, Anemarisis, another small Omommyid, possesses molars with lower, more rounded cusps and a reduced shearing potential, suggesting a preference for softer fruits. Tetonoids and Trogolemur appear to have occupied a middle ground, with molar morphology indicative of a more generalized diet encompassing both insects and fruits. These genera showcase the spectrum of dietary adaptations within the Omommyid family, from specialized insectivores to dedicated frugivores and those with more flexible, omnivorous tendencies. The enlargement of incisors, the front teeth used for biting and gnawing, presents another intriguing aspect of Omommyid dental adaptations. While not directly linked to a specific dietary preference for fruits or insects, these enlarged incisors may have served a variety of functions. In some genera, such as Stynius, the incisors are particularly prominent, suggesting a specialized role in food processing, perhaps for stripping leaves from branches or husking fruits. Alternatively, these enlarged teeth might have been used for grooming, much like the specialized toilet claw found on the feet of some Omomyids. It's even possible that incisor size played a role in social displays, with larger teeth signaling dominance or attracting mates. The exact function of enlarged incisors in different Omommyid genera remains a subject of ongoing research, but their presence underscores the diverse ways these early primates interacted with their environment and each other. The dietary adaptability of Omomyids undoubtedly contributed to their evolutionary success. Their diverse dental adaptations allowed them to exploit a wide range of food resources, from insects and fruits to leaves and perhaps other plant materials. This flexibility may have enabled them to thrive in a variety of habitats and potentially outcompete other mammals with more restricted diets. Furthermore, dietary specialization may have played a role in the diversification of Omommyid species. As different lineages adapted to specific food sources, they may have become reproductively isolated, leading to the evolution of new species. The remarkable diversity of Omomyids in the Eocene fossil record, with over 35 genera identified in North America alone, testifies to their evolutionary dynamism and their ability to adapt and thrive in the face of changing environmental conditions. Their story is a reminder of the power of dietary adaptation in shaping the evolutionary trajectories of species, a lesson that resonates even today as we explore the intricate web of life on Earth. Chapter 5. Whispers of Ancestry: Omomyids and the Quest for Primate Origins. Their primitive skeletal anatomy has complicated attempts to definitively link them to specific living primate groups. For instance, the stapedial artery, a branch of the internal carotid artery that supplies blood to the middle ear, passes through a larger canal in Omomyids than in modern haplorhines. Similarly, the path of the promontory branch of the internal carotid artery, another vessel supplying the ear region, differs between Omomyids and modern haplorhines. In haplorhines, this artery takes a perbular route, passing through the auditory bulla, a bony capsule in the middle ear. Further distinguishing them is the absence of contact between the allospheноid and zygomatic bones in the skull. The middle ear of Omomyids also lacks the anterior accessory cavity found in modern haplorhines. One of the most distinctive features of Omomyids is the presence of an aponeric, or hidden, ectotympanic bone within the auditory bulla. In Omomyids, this bone is uniquely positioned within the auditory bulla, a characteristic not seen in other primates. Some researchers argue that this unique ear structure represents a derived characteristic, linking Omomyids to a specific primate lineage. Others view it as a primitive feature, suggesting a more basal position within the primate family tree. The evolutionary relationships between Omomyids and later primates remain a subject of intense scrutiny and ongoing research. Three main hypotheses dominate the debate. The first proposes that Omomyids are stem haplorhines, representing an early branch of the lineage that gave rise to tarsiers, monkeys, apes, and humans. The second hypothesis positions Omomyids as stem tarsiforms, a group specifically related to tarsiers. The third hypothesis suggests that Omomyids are stem primates more closely related to adapids, another extinct primate group, than to any living primate. The fossil record of Omomyids, though incomplete, provides a rich tapestry of information. Tetoneus, with its large orbits, exemplifies the nocturnal adaptations of many Omomyids. Shoshonius, also with large orbits, may have possessed a suprametal foramen, a feature found in tarsiers, though its function in Shoshonius remains unknown. Necrolemur, with its fused tibia and fibula, showcases the leaping adaptations of some Omomyids. Microcheirus, another large-eyed primate, adds to the diversity of European Omomyids. Runia, with its comparatively smaller orbits, represents a rare diurnal Omomyid. Omomys, with a skeleton resembling that of dwarf and mouse lemurs, likely employed a different locomotor strategy than Necrolemur. Macrotarsius and Oroya, the largest Omomyids, demonstrate a shift towards frugivory and folivory. The discovery of Pseudolurus pyrenaicus in Spain revealed a transitional form within the Pseudolurus genus, bridging the gap between Pseudolurus isobinae and Pseudolurus parvulus. Necrolemur anedoni, also from Spain, clarified the evolutionary trajectory of the Necrolemur genus, linking Nanopithecus phyloli to Necrolemur antiquus. The recent discoveries of Oroya lamporia and Mytonius hobsoni in Texas and Utah expanded our understanding of Omomyid diversity during the Middle Eocene, resolving previous taxonomic confusion surrounding the genera Oroya, Mytonius, and Diablomomys. Further complicating the picture are genera like Teilhardina, Anemarisis, Tetonoids, and Trogolemur, each with its own unique dental and skeletal characteristics. These genera, along with others like Steinius, Lovena, Melanuremia, and Gemesius, contribute to the ongoing puzzle of Omomyid classification. Their varying dental morphologies, reflecting diverse diets, and their skeletal specializations, hinting at different locomotor strategies, make it challenging to construct a definitive phylogeny. The quest to unravel the Omomyid enigma is a testament to the power of scientific inquiry. Each new fossil discovery, each new analytical technique, brings us closer to understanding the intricate tapestry of primate evolution. The Eocene world, brought to life through the study of these ancient primates, reveals a dynamic ecosystem where diverse lineages experimented with different adaptations. By piecing together the fragmented remains of Omomyids, we gain a deeper appreciation of our own deep past, tracing the evolutionary threads that connect us to these small, unassuming primates that once thrived in the ancient forests of Earth. Omomyids, the earliest definitive primates, thrived across the northern hemisphere during the Eocene epoch. Their diverse dental adaptations reveal a range of diets, from insect ivory to frog ivory and folivory, while skeletal variations suggest diverse locomotor styles. The Omomyids' exact placement within the primate family tree remains debated, highlighting the ongoing challenge of interpreting the fossil record. These Eocene primates offer crucial insights into early primate evolution and diversification, raising fundamental questions about our own deep ancestry. Where do you think Omomyids fit in the primate family tree? Share your thoughts in the comments below. Like, subscribe, and suggest topics for future explorations. Never stop learning, for the journey of discovery is its own reward.